So I'll be talking about randomization, which is a topic which emerged in the recent year as a very promising topic for solving large-scale linear algebra problems. And this is a joint work with many people that I display here, some collaborators, some PhD students in the group, postdocs in the group, and software engineers in the group. And so I will start by describing what randomization is, and then I will focus a lot on how do we do one of the main operations when we use randomization, which is random sketching by presenting lower bounds on communication and then algorithms that will attain those bounds. And then I will explain briefly how randomization is used for solving linear systems or eigenvalue problems when we use Krylov subspace methods. What is our motivation? It's coming from the fact that when we want to use large-scale computers, we don't only face a very large cost of communication with respect to the cost of computing, but we also face an increasing heterogeneity, because if we were used to use double precision in the past, now we don't have much choice, but we have to use lower precision. And here is what you see, the performance in teraflops per second, looking at different generations of GPU. And what you see in red is the performance of FP64, which is down here. And what you see in blue is the performance of single precision. And if you use tensor cores with FP16, half precision, 16 bits, then that's exactly when we can gain when you switch to a new generation of GPUs. But if you are stuck with using FP64, then you might not expect a lot of improvement when you buy a new GPU. So it's becoming really important to use lower precision. And randomization is helping because it's reducing flops. It's also reducing communication. When we use randomization, we manage to have very simple communication patterns. You might be able to switch from +2 operations or +3. We'll see that it's also very suitable for employing misprecision, while we'll control the loss of accuracy, and we obtain numerical guarantees with high probability. And interestingly, sometimes we can solve some open questions, like, for example, if you want to do the LU factorization of a matrix and you worry about the gross factor, then if you pre-multiply with a random matrix, then you will control the gross factor. So I'll not be talking about this today. I'll focus more on solving linear systems, but let me first explain what's randomization. So it relies on sketching. It relies on embedding a high-dimensional subspace. Here, a subspace which lives in Rn, and then is going to be very large, into a lower dimensional subspace, which lives in RL, and L is going to be much smaller than N, while preserving some geometry with high probability. So it's been used in the last 10 years or so for solving least square problems, for computing the low rank approximation of a matrix. So SVD is replaced by the randomized SVD, for doing data compression, selecting a subset of columns, Krylov subspace methods, dynamical low rank approximation, and I'm sure there will be many more applications in the future that will benefit from randomization. And so more precisely, we say that we have a linear map, a random matrix omega, and this random matrix is going to be an oblivious subspace embedding if for any given subspace, m-dimensional subspace W, then we have with high probability, at least 1 minus delta, that if we take any pair of vectors, omega and omega prime, which belong to the subspace W, then we preserve their inner products. So if I compute the inner products between W and W prime, and then I compute the inner product between the sketches, which are vectors of small dimension, then the difference is going to be bounded by epsilon and the L2 norm of the two vectors. And so epsilon, we usually take it to be 1/2. And so that's why we say preserve geometry, it preserves inner product, distance in between vectors, it preserves the norm of vectors up to this precision epsilon. And so the first question we ask is, what do we pick as omega? And so there are different choices. And depending on our choice, the sketch dimension L will be changing. So we like L to be as small as possible while still preserving this side-space embedding property. And so in the following, I'll consider that we have M vectors, which are stored in a matrix W, and those are of very high dimension N, and then we sketch them by this matrix omega, and then we obtain the sketch matrix, which is of small dimension L by M. And we can take omega to be a Gaussian, so a dense matrix. So the entries will be independent standard normal random variables, which is rescaled. And then in this case, the sketch dimension L is on the order of epsilon to minus 2, M plus a logarithmic factor. And M is the number of vectors that we are sketching. So we see that the sketching dimension doesn't depend on N, it depends only on the number of vectors M. It's easy to parallelize because if W is a dense matrix, then we are just multiplying two dense matrices, and that's a very easy to parallelize operation. But if we look at how many floating point operations it performs, that's 2M and L. So it's linear with respect to the sketch dimension. And because we might want more accuracy, so we might want to increase L, then that's an active research topic to find some other structured random matrices such that we don't have a dependency on L here in the number of floating point operations. And a different kind of random matrix belongs to a class which is called fast transforms. So one such example is a subsample randomized Hadamard transform, which has this form here. So if we apply this matrix to a vector, first we apply a diagonal matrix which changes randomly the signs. Then we apply H, which is a normalized Walsh-Hadamard matrix, so it is a real analog with the fast Fourier transform. And then we draw L rows uniformly at random from the result, and then we rescale. In this case, the sketch dimension also depends on epsilon to minus 2, M plus a logarithmic factor multiplied with another logarithmic factor. So it's a bit larger than the Gaussian, but if we look at the number of floating point operations now, we have replaced L with log n, because that can be applied in the similar way in which the fast Fourier transform is applied. However, it's going to be slightly more difficult to parallelize and scale because we know that the fast Fourier transform is also more difficult to scale in parallel. And the third class of transforms that we can pick are called sparse subspace embeddings. In this class of matrices, what we do is that we generate independently each column of the matrix, and then for each column, we pick uniformly at random locations where we'll have non-zeros, and then these entries will be plus or minus 1 with probability 1/2. If we only pick only one non-zero, then this is called count sketch, but we can pick up to 4, 8. So very often in practice, 8 works very well. The sketch dimension in theory is going to be larger, so it's epsilon to minus 2m squared when I pick only one non-zero per column. But there are new results in which we can pick up to log n non-zeros, and then this m squared goes down to m log m, or a logarithmic factor multiplied by m. And so in this case, the number of floating point operations is equal to the number of non-zeros in the matrix W. So it's going to be cheaper. But this is a fundamental operation that we'll have to do when we use randomization. So if we want randomization to work well, we should be doing this first step very efficiently. And so this is why in the following minutes, I'll be focusing on how do we derive parallel algorithms for this random sketching operation. And then I will start with a result which was used in previous results obtained on communication complexities that focused on what's the minimum bound of communication that we have to perform when we multiply two dense matrices, A times B, and obtain a matrix C. And fundamental result here relies on the Loomis and Winnie inequality. And this result is used by interpreting the matrix multiplication, giving it a geometric interpretation in which we represent by a cube every multiplication which is performed in the three nested loops of the matrix multiplication. And on the faces of this cube, we have the matrices A, B, and C. And the Loomis-Whitney inequality says that if we look inside this cube and we take a set of points, so this will be some of the multiplications we are performing, and then we project this set on the faces A, B, and C, then we have that number of points here, V, is smaller or equal than the square root of the projections on the three faces. So in other words, this will allow us to bound the number of floating point operations we can do given some data from A, B, and C we have in memory. And the way these bounds are derived is by using an optimization problem. So we would like to minimize x1 plus x2 plus x3, where those three variables represent some amount of data a processor requires from each matrix A, B, and C. And we give some constraints. So the first constraint is the Loomis and Whitney inequality. And then the three other constraints represent the fact that we assume that the data A, B, and C is distributed over B processors, which also means that the load is balanced among processors. Because of course, if one processor will do the whole multiplications, then there will be no communication. So we want also the work to be balanced and the data to be balanced. And so that's a convex optimization problem, and you can solve it analytically. And we obtain results which depend on how many processors I have with respect to the sizes of the matrices A, B, and C. And this is what we obtain as a minimum amount of communication when we want to multiply A, B equals C. And we have three different cases. And those bounds also allow us to derive the communication optimal algorithms. And so, for example, in the first case, if the number of processors is smaller than m divided by n, where m is the maximum of the three dimensions and n is the median of the three dimensions, then we have to perform this amount of communication. And this amount is attained by an algorithm which is represented here. In other words, which says that if I have the three dimension in which one is large, but the other two are small, then what's the communication optimal algorithm would be the one in which I take the matrix B and I distributed it over all processors. So it's duplicated over all processors. And that's exactly the communication I will be doing. So I'll communicating the matrix B minus the amount which was already on my processor from the matrix B. If in the second case, I will have two large dimensions and one small dimension. In this case, A and B will be distributed by using a unidimensional distribution, while C will be using a two-dimensional distribution. And in the three case, we have three-dimensional algorithms in which matrices A, B, and C are replicated over processors, and the processors are seen as a 3D grid here. So those bounds allow us to know what algorithm will be a communication optimal. And now if we move to random sketching, we have a difference, which is the fact that now I am multiplying omega with A, but omega is a random matrix, and so I could generate it on every processor wherever I would need it if I want to reduce the communication, given that the generation is not going to be more expensive than the communication of the matrix omega. And so we take advantage of this, and so we have a new optimization problem. I'm going to minimize over only two variables because now I want to minimize the amount of communication I will need from A and B, but not omega. And I will have, again, constraints. The first one is, again, coming from Loomis and Whitney, and the other one are coming from the fact that we want A and B to be well-balanced among processors, and the communication and the computation as well to be well-balanced among processors. And if we solve this problem, we also have 3 different cases, depending on the number of processors and on the dimension of the matrices A and of the scale dimension L, which will give me the matrix omega. And so if we solve this problem, then we obtain the following bounds of communication, which will tell me that if the number of processors is smaller than the number of columns in the matrix A, then I would need no communication. And then we have 2 other cases in which I will need some communication. But let me show you with an example what happens in those 3 cases and how do we derive the algorithms that will attain those lower bounds. So in the first case, which is represented here, the number of processors is smaller than the number of columns in the matrix A. So to not communicate at all, what I would need is to distribute A by a block of columns among processors, generate omega on every processor, and then compute columns of B with no communication. So this will give us an algorithm which requires no communication, but for this, I had to generate omega redundantly on every processor. In the second case, if I have more processors than columns in the matrix A, then I will also have to distribute the rows of A among processors. And then omega will also be seen as a 1D distributed matrix, and B will have its block of columns distributed among processors. And this algorithm will allow me to attain these lower bounds of communication. In the third case, I have quite a large number of processors, and then I'll have to distribute by using a 2-dimensional distributed omega and B, and so we get back to having a 3D algorithm. And the advantage of seeing algorithms in this way is the fact that I could write a 3D matrix multiplication algorithm, which, depending on the dimensions of the matrix and the number of processors, it will be falling in the first case, the second case, or the third case. But we will see it here in the last case, the 3-dimensional case, in which what we do is that we have the processor distributed as a 3-dimensional grid, P1 by P2 by P3. And then on one face, we have the matrix omega. On the upper face, we have the matrix A. And here on this face, we have the matrix B. And we now write the algorithm such that each processor is responsible for a cube of the computation. When we start the algorithm, we consider that A is distributed in a balanced way among all processors. So if I look at this processor, it will only own at the beginning a part of this square here. And then we'll write the algorithm such that omega is generated whenever is needed on any processor where is needed. And then we'll be calculating B in the following way. So at the very beginning, we started with just on my processor having a part of the matrix A. And then the very first step will be to communicate A among the processors along P1 such that this processor here receives and owns this entire part of A. This part of A will be redundantly now owned on the processors along P1. Once I have this part of A, we generate this part of omega that I will be needing on this processor. And then the processor will compute this multiplication locally and get one term of the computation that will be required for this block of B. The other terms are computed by this processor and by this processor. Once every processor did the computation, then we need to do a reduced scatter along P3 to sum up and compute the final block of B here. So that's the 3D algorithm. So the communication which are involved are an all gather to obtain the block of A I need, then the generation local of the omega that the processor needs, and once the local computation is performed, then a reduced scatter across P3 to compute the block of B from the terms which are computed by every processor. Now, if I would pick P3 to be equal to 1, then there will be no reduced scatter of B. If I would pick P1 to be equal to 1, then there will be no all gather for the matrix A. So this algorithm works for all different kinds of grid configurations. And then let me show you what we obtain on GPUs. And so those are results obtained by Johannes Laute on the CSCS supercomputer in Switzerland. And what we presented here are the results for the sparse hash matrices for which the theory can be adapted. So I have presented the theory for dense matrices, but one can adapt it and obtain the theory also for sparse matrices. And so the first results in blue are for the sparse matrix when we take only one non-zero per column, which is called count sketch. Then we take 4 non-zeros, 8 non-zeros, and that's the sketching obtained when we take the matrix to be dense Gaussian. We increase the number of GPUs from 1 to 64. And then we also present for each result performance obtained by the algorithm which generates omega to avoid the communication of omega, and then the 3D matrix multiplication algorithm which will communicate omega whenever will be just a classic 3D matrix multiplication algorithm. And then what you can see is that the algorithm scales well, and we obtain improvements by the version which avoids the communication of omega, particularly when the number of GPUs is larger and the communication is more important. And then in particular in this case, for example, for count sketch, there is a large factor of improvement of 5, while for dense matrices, the factor of improvement is 1.7. And the factors around 2 are obtained for the other random sparse matrices here. Those results are for a square matrix, and those results are for a tall and skinny matrix, where we have 512 columns and 221 rows, and the sketch dimension here is 2048, and here is 4096. And sorry, I think the factor of 5 was obtained here for the tall and skinny case, where the communication is even more important. Another result, also on GPUs, but up to 16 GPUs, also includes a subsample randomized Hadamard transform. And that's a big debate in the community, because part of the community will say, we don't care about the fast transforms because the sparse matrices are the ones which are the most performant. But if you implement really well this subsample randomized Hadamard transform, then in the tall and skinny case, where we have few columns, we have observed that that's the one which is the most efficient. So in this case here, we present the count sketch, so 1 non-zero per column, sparse size with 8 non-zero per column, and that's a subsample randomized. And we see that consistently it's the transform which is the fastest here. So with this, I'm finishing the first part, which is on how to sketch efficiently and in parallel. And then I'll be moving to the second part, in which we will see an example of how this is used in Krylov subspace methods. And when you do linear algebra, one of the operations which is really the bottleneck is the orthogonalization process. We are given a matrix which is tall and skinny, and I get back to the notation from the beginning. So we are given a matrix W, and you are given this sometimes at once or sometimes vector by vector. So I'll consider particularly the case when it's given vector by vector, and we want to compute basis for this matrix. Typically, we would compute its QR factorization, where Q is orthogonal. But that's really the bottleneck in many situations. And so our goal here was to use randomization to speed up this process. And what is a very nice property of those sketching matrices is that if I'm computing, if I'm taking omega to be an oblivious subspace on the embedding for the subspace spanned by the columns on Q, then we know that with high probability, the condition number of Q is smaller than O of 1 plus epsilon, the condition number of the sketch of Q. And what we can observe here is that if I will have an algorithm for which the sketch of Q is orthogonal, then I will obtain a matrix Q, which is very well conditioned. And in many algorithms, we don't need Q to be orthogonal. We just need it to be well conditioned. So that's sufficient for many, many cases. And that's exactly what we are going to do. So we are going to derive algorithms where if I look at the sketches of Q, those are L2 orthogonal. And if I look at the vectors in Q, they are not anymore orthogonal, but they are not far from orthogonal either. So the condition number of the basis is really very, very low. The idea comes from a paper by Rocklin and Tiger from 2008. And then in 2020s, then it regained attention in the context of Krylov subspace solvers. And so what we could see from here is that if I'm sketching W and I'm computing the orthogonal factorization of this small matrix, then I will obtain this R factor, which in infinite precision is the same, and then I will obtain a small s factor, which is a sketch of Q, and this one is L2 orthogonal or orthonormal. So that's the idea we are going to use, and we have used it to derive first the randomized Gram-Schmidt orthogonalization process in collaboration with Oleg Balabanov. And how this works, so this replaces the classical Gram-Schmidt or the modified Gram-Schmidt. And the main idea is to replace the orthogonal projector, which is used in Gram-Schmidt, or the approximation of the orthogonal projector with a projector which is orthogonal with respect to the inner product induced by omega. So in other words, at each step of the orthogonalization, we are given a new vector Wj, and then we use this sketch orthogonal projector to obtain the new vector Qj. And so this sketch orthogonal projector, what it does, first it sketches a vector, then it solves a least square problem with a sketch of the basis, and to compute the coordinates of the vector in the new basis, and then it multiplies with Qj minus 1 and subtracts from the identity to obtain the new vector Qj. And here I'll just explain why I was saying that that's really an approach which is suitable for mixed precision. Is because once we have sketched the vector, we have a very small problem. For this very small problem, we can use FP64 because we can use, it's a small problem, so we can use higher precision. You can use whatever is the most accurate least square solver. So typically it really relies on householder QR. But then when we go back into the high dimension, so we will multiply here with a large matrix, then we can lower the precision. We can use FP32 or FP16. And randomization more generally than here, it's really well adapted for mixed precision because once you did the projection into a lower dimension subspace, we have a small problem to solve, then we can solve it in FP64. But whenever we solve in high dimension, then we can use lower precision and we still obtain stable algorithm. And then what's nice here is that we can show that with mixed precision, the condition number of the computed Q factor it has this dependency on epsilon and then dependency on the condition number of W linearly, and then also a dependency on M squared. So this is a result which somehow resembles a modified Gram-Schmidt, even if the error is measured differently. But in modified Gram-Schmidt, you also have a dependency on linearly on the condition number of W, and then on the M, but also the N dimension. So in some sense, this result is even better than for modified Gram-Schmidt. We got rid of the dependency on the large dimension because we have computed here on the small problem, the coordinates of the vectors. I will also show you a bit randomized householder QR, just to say that in nonlinear algebra, if we really want to be precise, then we use householder QR, because in this case we can compute the basis which doesn't depend on the condition number of W. And this can be transferred into a randomized version. And so the randomized version, what it does is that it obtains a representation of the orthogonal of the Q factor. In the householder QR, the representation of the Q factor depends on the so-called householder vectors Y, which are represented here, a square matrix T and Y transpose. So when we apply Q to a vector, then we would be performing this operation. In the randomized householder QR, we obtain a representation in which the second term depends on the sketches of the householder vector. So when we apply this representation to a vector, we first sketch the vector, then multiply this with the sketches of the householder vectors, multiply with T, and then back a multiplication in the high dimension. And so with this representation, we have reduced the number of flops, and the condition number still remains independent of the condition number of W. And so it remains a very stable operation. And just to wrap up this part, I will show you a few results on the numerical accuracy we obtained for these operations by presenting here in the two graphs results obtained if we would use only 32 bits, and then results if we would mix 16 bits with 64 bits. So 64 bits whenever we have a small problem and we solve it accurately. And then we build a matrix such that when we arrive around the 300 vectors, and this matrix becomes singular. And then if you would use classical Gram-Schmidt, then the condition number of the basis will explode. If you would use modified Gram-Schmidt here, then the condition number will increase, but will remain reasonably low. While if you use randomized Gram-Schmidt, then the condition number remains very low here. And randomized householder QR, then it remains really around 2 or 3. So it remains really very well conditioned. When we mix, we also obtain very good results. So here we only present randomized Gram-Schmidt in blue and randomized householder QR in red. And so for the randomized householder QR, we see that we have still a small condition number, and randomized Gram-Schmidt is slightly larger, but still a well-conditioned basis. And how this can be done in Krylov subspace methods. So when we want to solve a linear system, what we do is that we start from an initial guess, x0, and then we build a Krylov basis, which is a basis spanned by the initial residual R0 and powers of the matrix A multiplied with this initial residual, while imposes two conditions, the subspace condition and then the Petrov-Galerkin condition. So impose that the residual is orthogonal to a well-defined subspace. And for example, if you would use GEMRES, then this subspace will be A multiplied with the Krylov subspace, and then GEMRES will find the solution by minimizing the residual over x0 plus the Krylov subspace at a given iteration. When we use randomization, we replace this Petrov-Galerkin condition with a sketched Petrov-Galerkin condition. So we impose that the sketches of the residual are orthogonal to the sketches of the vectors in the subspace LM. And what does it mean? It means that when we do GMRS in the orthogonalization process, we replace Gram-Schmidt or householder QR with a randomized Gram-Schmidt or randomized householder QR. And this will allow to satisfy the sketched Petrov-Galerkin condition. And specifically in GMRS, now when we find a solution by minimizing this L2 norm of the residual, in the randomized version, we minimize the sketch, the L2 norm of the sketch of the residual over the Krylov subspace. And we have also worked on integrating these ideas in different applications. And here I will just show a result from material science in density functional theory, where they run a self-consistent field iteration where they solve a digitization an eigenvalue problem. And we have replaced the eigenvalue problem, which uses log-PCG, with a randomized Jacobi-Davidson version. And then we look at the convergence of this method over the iterations for two different systems. And what we observe here is that it either behaves as log-PCG or sometimes it can behave even better. So it can be even more accurate. So with this, I have arrived at the end of my talk. So just to say that all those methods we are implementing them in a library, which is called RandMixPack. So those different sketching techniques, but also the orthogonalization and the linear and eigenvalue solvers that we have developed. And with this, I will be happy to take questions.
Yeah, thank you very much. So we already have some questions. So if you want to ask questions, you can either write into the question and answer section, or you can raise your hand. We already got two questions during the talk. The first one by Vladimir Getov, who asked, I guess floating point performance results are for experiments on systems working with the IEEE 754 standard. Could you share views about solutions at architecture level to address a problem such as the POSIT arithmetic proposal? Laura.
Yes, so yeah, that's sort of an open question. It's it's a moving target because those new formats come up, keep showing up. Of course, we prefer to work with standards, but then we have to adapt to whatever is most efficient on the current architectures. And
okay. Yeah, thank you. Yeah, I think it's very difficult. I mean, we see some standard formats, standard non-IEEE formats for these, especially the very low bit number floating point numbers. But I think we have to see where this goes. The next question is from Andreas Statopoulos, who asked a question that also came to my mind. He says, is the possible dependence of random omegas generated on different processors a problem? I think this corresponds to slide 14. And I understood that you produce the same omegas, right?
Yes, so we use a counter-based random number generator such that you can produce from a given seed the same omega on different processors. Yes.
Yeah, okay. Yeah, that's what I thought, that you use the same initialization of your random number generator, essentially, right?
Yes.
Yeah, okay. Then we have Andrew Kniazev, who asks, why randomize Jacobi-Davidson rather than LOB-PCG itself?
Yes, so we would love to randomize log-PCG itself, but it's not easy at all because when we give up on having an orthogonal projection, then we don't recover any more accuracy. So we don't have a solution for randomizing log-PCG, and typically it's very hard to use randomization for short recurrence like conjugate gradient, and log-PCG also have a somewhat specific basis. So in this case, it's really hard to use randomization. So it's an open question how to use randomization for log-PCG.
Okay, so the next question is by Rachel Jovel. She asks, on slide 20, you assumed that the matrix is given vector by vector. How would the approach change if it is given at once?
So if it is given at once, indeed, there are better solutions, particularly if the matrix is well conditioned, then you can just sketch it, compute the QR factorization, and then you get the R factor and you multiply with basis with R inverse. So it's a bit like a randomized Cholesky QR approach. if the matrix is well conditioned, then you could do this and it could be more efficient.
Okay.
But if it's badly conditioned, then randomized Gram-Schmidt or householder QR will still be more stable. Yes. But when it's given vector by vector, you don't have this more efficient version.
I see. Thank you. So the next question is by Michael Roux, who asks you, who you mentioned FP16. Do you see that BF16 has a role?
Yes, so that's again something that we will see what the future decides.
I see.
But
okay.
From our point of view, it's more we have to use 16 bits. How can we use those 16 bits efficiently? And so the approach I was explaining is that if you know in an algorithm which part is really important to do in higher precision, then you can mix like this. And randomization, it's really nice that you project, you get a small problem, and it turns out if you solve that small problem in higher accuracy, then the other operations you could do is 16-bit. And I think it could be FP16 or it could be some other format. But the approach will remain the same.
Okay, thank you. Then there's a question by Bram Meach, who asks, in the GMRS algorithm, the norm you minimize includes omega. How does the norm of f minus ax without the omega behave? That is, how does the spectrum of omega look like?
So the spectrum of omega will really depend on the choice you are making. If you are taking a Gaussian matrix or subsample randomized Hadamard transform or the sparse sketching. So it really depends on this, but the theory will tell that this, if you can prove that your choice in the oblivious subspace embedding, then you have all these geometry preserving properties that are very helpful for linear algebra.
Okay, thank you. Then there's one question by Jason Reddy, who asks, machine learning, AI, deep learning uses positional encodings like ROPE that mostly preserve L2 distance between input tokens and lower dimensional encodings. Do you know of any work comparing, contrasting these or items like traditional ML kernel tricks?
No.
Short answer for your question.
We wrote an overview that looked at different approximations in the attention mechanism. And there are a few works that aim at using randomization for speeding up the attention mechanism, but I don't know of any work contrasting these ideas. Yes, but that's an interesting topic.
I see. Thank you. Then there's a question by Carmine Hochfeld, who asks, in the first part, performance results were shown for count sketch, sparse sign, and subsampled Hadamard transform. How do these sampling matrices compare from a numerical point of view? So, yeah, there is a difference in between the theory for which the Gaussian has the optimal sketch dimension, then subsampled Hadamard transform, and then count sketch, where you would think that your dimension should be number of vectors to the square. And now if we look from a numerical point of view, then in many situations, if we take 8 non-zeros per column, we obtain results in accuracy as good as a subsample Hadamard transform and almost as good as a Gaussian. But of course, you can come up with examples where for the sparse science matrices and the sketch dimension could be larger. But on average, they seem to behave quite similarly. Thank you. And then there's a question by Vincent Melou, who asks, on the DFT application, you show better convergence behavior with the randomized approach. Do you observe speed up to the converged results?
So we are implementing now all of this on GPUs, and of course, getting speed up is not always very easy. So it turns out on GPUs, non-symmetric eigensolver, it's much slower than the symmetric eigensolver. So to get to really get some speed up, we had to do some tricks to get back to a symmetric eigensolver, and the hope is that we will get speed up, but our even better hope is to use mixed precision.
I see. Then there's a question by Robert Ernstbrunner, who asks, any thoughts on deterministic sketching ideas, so instead of using randomization?
No, that's a hard question. I don't have many ideas. I don't have many thoughts on this.
Yeah, I see. Okay, this seems to have been the last question. So Laura, I thank you very much for presenting your work here in the Supercomputing Spotlights. I thank all the participants for taking part in this. We had more than 130 people attending this at the peak. We will have other Supercomputing Spotlights in the future. Let's thank Laura again, and I hope to see you all again soon, either here in the Supercomputing Spotlights or in person. Thank you for coming. Bye-bye.
Thank you. Bye-bye.